Okay, so welcome back to week 3 of Introduction to 3D Printing. Thank you to everyone who sent assignments. That's been great. It's a lot of fun, sort of like messing around with them and seeing what you printed, and getting a window into sort of the thought process there. That's been really great, actually. So I've been really enjoying that. Okay, so let's just get straight into it. So what are we going to cover this week? So this week we're going to review some of the submissions from last week. They were pretty great. And then what we're going to really sort of get stuck into this week is going to be another design one, and it's sort of a counterpart to a counterpoint to what we did last week, where last week we were looking at designing for art, and this week what we're going to do is we're going to have a look at designing for function, right? So how do you make things that move? How do you make things that do things? So within that, we're going to have a little bit of a look at some modeling and material choices, have a look at the design of some sort of basic mechanisms, and use that as a setup for, maybe, I think as we go, we'll sort of I'll explain the mechanisms within Tinkercad, and then I'll use that as a setup for the assignment this week, which is also going to be building a basic mechanism. Okay, so let's have a look at some of the assignment submissions from last week. They were very varied and very interesting. Okay, so let's have a look at this. So first thing I want to have a look at is actually Sheila's submission here, which I thought was fascinating. So this little cage structure here, I didn't actually end up printing it for interesting reasons, and I'll go into sort of why they are. So this structure here, on the box, seems like it would print really well, right? So the actual thick parts of these tubes, they've got very modest angles coming up off the build plate. They'd print quite nicely. They'd get a lot of detail. They would print really, really well. The base here especially would work really well on the build plate. And even though you've got rounded edges, they'll sort of come up quite nicely, and it'll end up being sort of quite a nice print. But where it gets really interesting are these star shapes, which are in the center of each side of this the pentagon, and they are actually fairly thin. And if you'd printed them just flat on the build plate, you could probably end up with a pretty okay result, actually. But when they're angled up like this, you get a really strange interaction with the slicer. And let me show you how that looks. So when you start slicing it, what you end up with is this artifact just here. So you can see what's happened is that the center of the stars, there's enough thickness to sort of render the shapes, but the edges of the stars are so thin that it doesn't know what to do with them, and it ends up sort of basically just not printing them at all, right? So if we tried to print this, it would end up basically air printing these stars, and we'd basically get spaghetti for each one of these stars when it sort of tries to print these, even though the rest of the structure would print. It'd be actually, might be kind of interesting to sort of run that through and see what happens. But so you can see that even though the if the star was basically pointing straight up, it would have printed, or if it was flat down on the plate, it would have printed. But even at sort of a relatively modest angle like this, really thin shapes become quite problematic quite fast. So that's something to sort of consider when you are going with shapes like this. So the solution here is twofold. So one of the things that two primary options that I see, right? So if you're working with a model like this and you wanted to make the stars more printable, if it was important to print this all in one go, I'd make the stars thicker, right? So I'd basically get it so it was approaching the thickness of the tubing that was maybe half the thickness of the tubing that's around there, and that would probably be thick enough for the slicer to be able to see it and print it. But another thing that you could do that would probably work better, and this is something we're going to cover next week, is that I'd actually print out the stars separately. So you'd print them out as separate items, and then you'd have it so that they would either click into place or snap into place or even glue into place. And that's probably the best way of handling that particular problem. But it was a very, 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 very cool design, and it'd be really interesting to sort of try to make this work. And I love the sort of the repetition of this, and it's a cool looking thing. It's just it's not quite ready to print as it is. So yeah, there was that. Some of the other assignment submissions were also fun and interesting. This was another great submission here. Another interesting one that actually probably needs to be split into pieces before we print as well. Partially because it's got this same problem of these fine detailed sort of like nubs which are hanging down, right? And because they're hanging down, the detail on the bottom of these is probably not going to be great. So if I was printing this, I'd probably actually print the hand separately, and then I'd take this corona sphere, for like a better word, and then I would split it in two. So I'd take that whole hemisphere and I would just split it in two. So the flat side of each hemisphere was down on the plate. And if you did that, then each flat side of the hemisphere would print out separately, and then you can just like glue, or again, like, and we're going to cover it next week, like try to figure out how, you maybe put some pins into this so you could assemble it separately and put it into place. The nice thing about doing that as well is that if you wanted to paint that separately, if you had those separate pieces, you could print out like, the virus molecule separately, paint that separately, paint the hand separately, and then assemble it together, rather than trying to sort of paint it in place, which can sometimes get a little bit hairy. For any of you who've done sort of like trying to paint in very small pieces, that can get a little exciting. So that's a way of sort of working around that. This assignment submission, Chris, was great. So this is Totoro, for those who are familiar with him, who's being kit bashed with several interesting components. My absolute favorite is the Nokia cell phone hammer that he's holding. It's pretty great. So you can see his arms have been removed, and he's been given beefy arms, but in very novel ways. And he's even got like a Game of Thrones shield, as far as I could tell. And he's on like this fire sort of like base. It's really, really, really cool. And we'll get to that in a second. So that's a sort of like a good example of like, how you can assemble these together. And this is actually it's a good point to sort of like switch over to actually having a look at some of the prints, right? So I'm just going to take these out right now. And these were interesting all on their own. So let's start with Totoro. So this is how he came up, and he looks very much sort of like a sort of a D&D miniature. Let me see if I can focus in on him a little bit better. There we go. So he's looking very much sort of like a D&D miniature here. So the lighting here isn't very sort of like forgiving on the poor guy. But what I've done is that I've printed him out, but I've also left the supports on there. And to see like, okay, so you can see you've got the raft on the bottom of the model here that we'd snap off. And then we've got the supports under his arms. But if you look at this support here underneath the hammer, it's actually quite revealing. So when this got printed, the hammer was actually quite thin. And the handle itself is extremely thin. So it's probably only about sort of like maybe 1 to 1.5 millimeters thick. And when we have that, it meant that for example, when I tried to snap the support off, what actually happened was that the hammer snapped here instead. And this was sort of like, I probably could have avoided this, but I wanted to illustrate what happens when, you have these sort of like thin pieces that are floating in space. So again, sort of like touching back on sort of the model slicing thing again, which we're going to go into a little bit more next week. The way to handle that was that you'd probably actually print out all these pieces separately. So you'd print out the hammer separately. You'd probably print out this arm separately. Maybe even the shield came out surprisingly well. I wasn't sure how that was going to work, but you maybe even want to print the shield separately, and then you'd actually then glue them together later on. And that way you can avoid a lot of sort of like the strength issues that come up with this. And you can also sort of be a little bit careful about how you orient things to maintain detail. And these pieces which got submitted were super cool because they were designed in such a way that they would print quite naturally and quite well. So the way they were oriented on the build plate was like this. So you can imagine like in the base of the table here is the build plate, and it went straight up from there. But if we look at the sides of these, there's actually a nice amount of detail. So there's like a little line here along the middle. There's even these like little cutout inserts, which you can just sort of barely see in the light there at the base. And because there weren't any overhangs, they both printed out really, really, really well. And even at a coarse resolution, the models look really great. So, one possible solution here is to sort of like understand what your printer does and understand the orientation and work with it when you're generating your models, when you're generating your designs. And just to sort of like close up the thought on kit bashing, I know we put beefy arms on Yoda last week, but that's what it looks like. So that's what he looks like finished again. So I did like a super tiny quick print, but it's just a little bit illustrative here to sort of see. If you look at the base of his ears just here, you can see that they're a little bit rough, and that's where the supports were. Also, the bottom of his arm here as well, you can see there's a little bit of roughness there as well. And that's an illustration of what happens when you have the supports and you're trying to figure out, how many supports I should use, like where should I place them. and what's that going to do to my model quality? So, it's lucky that the bottom of his ears aren't that interesting, the bottom of his arms aren't that interesting, and having a go with sort of progressively finer sandpaper to fix that is totally a doable thing. And a question which came up a little earlier today was, what happens if you increase the model size? And I thought it was actually really good, right? What happens in terms of the model size? How do things change when you have, let's just say, like, you take your model and you make it a little bit bigger, and if you make the model a little bit bigger, what happens to the the quality of the print on the underside? So one way to think about it is that if your supports are, say, 0.1 millimeters thick, and you scale your model up, your supports are still going to be 0.1 millimeters thick. So the actual size of your support, the amount of contact the supports have with the base of your model, becomes less. So generally speaking, the bigger the model, the more detail you can have, especially on the undersides of things. I should have paused for a second, Amy, before I go to the next session. Amy, you had a question.
Yeah, I mean, maybe you're going to cover this, or I missed it last week, but when I just got around to trying to do this assignment this morning, and
Sure.
um, and I noticed a couple of objects that I tried to use.
Mm-hmm.
Every time I would pull them over to try to place them, I had like an egg, and I was going to put a pair of glasses on it.
Nice.
But every time I pulled the glasses over, it put it behind the object, and I couldn't figure out how to pull it forward.
Right. Okay.
This happened. Yeah.
So how to move stuff around on the build plate. So I'm going to use Totoro here
Well,
as an
yeah,
example.
yeah. I mean, it was. I mean, I thought I knew how to move stuff around, but it's like, what is it with this? Yeah,
If
yeah.
Okay, so I'll tell you something quirky and interesting about 3D interfaces, right? So this is a problem that is, but there's this particular bug that I think most other tools don't handle particularly well, right? So what happened is that if you are, and this is actually not a bad practice. So let's just say I want to move this cube around on the plate. Generally speaking, with most 3D applications, if you want to accurately move it, what you do is that you change the camera so that you're looking down on top of it, right? So when you click on this guy, so I'm just holding down my left mouse button here, and I drag, the object will stay pretty much right underneath the cursor, and it will go exactly where I want it to. Now, this is where it gets weird. So if I then am looking from the side here, when I move this, oh my god, all of these like very small movements get magnified into huge movements, so it ends up zooming around, right? So this is a classic problem which has existed in 3D software forever. Generally speaking, if you want to more accurately place things, just go and look above it, right? And it's the same thing with, like, if you want to move this object up and down as well. You basically want to be perpendicular to where it is, right? So if I want to move this object up and down, just look from the side, and you'll probably end up with more accurate placement than if you try to do the same thing when you're looking from above, because it's really hard to see what's sort of going on. That's fair enough. One thing that might help actually is hiding and showing objects, right? So what I'm going to do is I'm actually going to show you an example of that, right? So let's just say I've got this cube here, and then I'm going to make this big, right? So I've got this giant cube here. And what I'm going to do is that I'm going to drag a cylinder into the scene, and oh no, I've placed the cylinder inside, right? So what am I going to do to get this cylinder back? So a really good tool here that you can use is that if you click on the box, and there's something hidden inside it, what you can do is that you can hide it. So there's this little light bulb icon. So if you click that, it will hide the box. So then if you want to get all the hidden objects back, what you do is that you hit the show all button, and that will bring it back. So if you have stuff that's potentially inside other objects, it's a good way of discovering them. The trouble with the show all button is that it will show everything. So if you've just hidden a few things and you want them to stay hidden, it's kind of difficult to keep them that way. There may be another way of doing this in Tinkercad, but I'm not familiar with it. So yeah, there's that. So, okay, cool. I hope that helped. Yeah, yeah, pretty much. Just fiddle with it and you'll get there. I'm fairly confident about that. Cool. All right. Well, look, since I'm here, let's talk a little bit about. I'm going to switch back to talking about designing for function. So let's have a look at that. So I'm going to switch back to my. Let's just switch back to me just to start with. So one of the things that I found really satisfying about 3D printing is that I live in a not very big place in San Francisco. I don't. I would love to have a workshop. I would love to have a tool shed, but I have none of these things. So I had a really bad itch that I needed to scratch about making things, and I just couldn't. And 3D printing really fixed that, and that's been a delight. And it's been really nice making things that solve problems that I have that are actual physical objects, right? So one of the sort of like very on topic recent examples has been a fix that I had for face masks. So for those of you who are familiar with what happened in California a couple of years ago, we had very bad wildfires, right? So when we had the wildfires, we were able to get sort of like respirator masks long before coronavirus was a thing. And these N95 respirator masks were great. And this particular brand called Vogue mask were extremely popular. They're quite comfortable, they were washable. But the issue that they had was that these masks had valves. And during the current crisis, that's not great, because if you have, the whole point about wearing a mask is that one half of it is that so you don't get so much breathed at you, and you're not going to inhale as much, but it's also to prevent you exhaling. If you potentially have like COVID asymptomatically, you don't want to breathe on other people. So if you have one of these valves on your mask, it's going to be you're walking around and you're just spewing your air all over other people. It's not a very kind thing to do. But we had these masks and they were really great, and we wanted to figure out how can we continue using these. So we needed to come up with some sort of cover for this valve, right? So you can see it's got this inlet at the back here, and we've got this valve on the front where it's really sort of exhaling air. So I not only needed to cover this, but it needed to be a fairly strong visual indicator. It's like, hey, this thing is closed. It's all right. I'm not going to breathe on you. So I spent some time designing a little clip-on cover which went on that. So that's what this little guy here is about, right? So what it is that it fits the little teeth here are it's not super clear, but they actually fold in just a little bit so they grip. And so what I did was that I was there with the calipers. One of the tools in your tool set that I would highly recommend getting is just a cheap pair of calipers. So these are like little brass calipers that I got. I got this for like $5 online. They're really not hard to get. And I basically spent some time sort of like measuring. Awesome. I spent some time sort of like measuring this here. I had a look at. I had actually made some guesses about the angles, and then I use that to sort of design this little clip-on cap. And what do you know? It works, right? So, I take this little clip-on cap, and it just sort of snaps on fairly nicely once I match everything up. And this sort of like fits on nice and tight now. I can easily take it off if I really need to, but it doesn't come off unless you like put a fair bit of force on there. I even got like a little groove here so that you can put on little decorations if you want. So like my daughter uses this and she's got a couple of different like face caps which you can put on this. But this was like a good example of something that you can do like just at home, sort of like relatively quickly. So this was a few afternoons worth of design and iteration. It obviously didn't. I mean, with a lot of these, they don't work straight up, so you need to do like a few prints to eventually get it to sort of where you want to. But it was totally a feasible thing, right? And it's totally a thing that you could do at home. Um, Another thing that I did that I'm currently using, like right now, is that I designed a microphone stand, right? So that's what this little thing here is all about. So what happened was that I had quite a nice microphone that wasn't really. It was sort of meant to be sort of like an out and about, sort of like roving microphone, and but but it wasn't really designed to be sort of like used as a desktop thing. So I ended up, I wanted to sort of figure out, is there some way that I could continue to use this? So I also had some PVC piping that was lying around, and I thought, okay, so is there some way that I can combine this sort of like random bits of PVC piping, and can I convert this into a microphone arm? So that's what this little guy here is about. So I'm just going to move the camera over just for a second to the overhead camera view. Okay, so that's what this is all about here, right? So I've got I got the microphone here, and it's sitting in it. The vibration isolation is provided by literally by rubber bands, and it's sitting in a ring here. So I put little teeth on this so it would sit quite comfortably. But then what I've got is that I've got these little teeth that I made. So these circular sets of teeth, and there's literally a printed nut and bolt. So I'll show you one of those in detail in a second. But those little printed nuts and bolts are there, so I can basically change the pose on the arm, right? So I can take these and I can adjust them to sort of wherever I need to be. So you can see how it sits sort of just here, right? So we've got one arm part of the pose there, coming back up here, it sets it over there, and then down here to sort of where the microphone is. And that was extremely satisfying because I didn't I didn't want to spend any more on like getting a new microphone because the one I had was pretty decent, but all I needed was a vibration isolation and a way to sort of like place it somewhere. So that's what the that's what the that's what the job was. But we needed to be able to design some sort of like posable component for it. So that's what this little sort of tooth design for was, right? So I'm just going to undo this a little bit. So everything is plastic. I wasn't even certain this was going to work, but it worked really well. So it's a plastic nut and bolt, which I printed. So I think I might have showed you this a couple of weeks ago, but it's totally possible to print sort of like fairly detailed nuts and bolts on I was doing this on my previous printer, which was pretty cheap. And there's more than enough detail there to sort of print these functional nuts and bolts. But where it gets interesting then is these components which are designed so that you can basically move them together, and then if you want to change the pose, you change the pose and then you use the nut and bolt to tighten them so that you can get it into sort of any like rotation angle that you like. And that was an extremely satisfying design iteration, and it was a nice way of especially now that we're all sort of stuck inside and it's harder to get things sometimes it's nice to be able to effectively just use up what you've got in the house, right? So that's the function of this sort of design. So designing tools, designing functional things, and making them, there's a real sort of like satisfaction that comes out of that I think 3D printing gives you access to in a very sort of like a quick sort of satisfying kind of way, which I really liked. Please. No, please go for it. Right, got it. So it was important for the teeth to be correct. That was like that's how it had to look. Because if the teeth weren't correct, that's where all the dimensional accuracy needed to be. So the orientation on the plate was like this. I'm going to switch back over to the overhead. So it was like this, right? So you can imagine the base of the plate here, and then we printed up from here. Printing on the side wouldn't have worked because you would have ended up with dimensional problems. Actually, we're going to get to this in just a second. Printing this way, obviously, we would have ended up with a hole supports in the middle of it. And how this looked on the outside didn't actually matter all that much, right? What was really important was that the thing that I wanted to maximize was I wanted to maximize how it gripped on to that part of the mask. And actually, go.
Sorry, the second question was because this is one of the things I have this stupid thing that I've been wanting to make, which is I bought this great beard trimmer, right? Which I love. I use it at home all the time, except it has a really big design flaw. As soon as I put it in my beauty case, in my travel bag, the button that turns it on is very sensitive. So it happened to me 3 times that I travel, I get to my destination, I don't have a charger. It has a stupid one of those one-off charger plugs, so you cannot find an alternative charger, and its battery is dead because, of course, it was running for the entire flight, right? So I wanted to build a cover for it, but the shape of it is one of those nice organic shapes that I was like, okay, with the caliper, how do I find something to wrap around it? And it was, I haven't yet found a
There's actually 2 things that you can do here.
I thought of photogrammetry as one.
No, you don't actually have to go. It doesn't have to be that sophisticated. There's a real cheat. I think I showed in the first week, I showed a finger brace that I had. So what happened was that I previously had like a knuckle strain, and if I don't show it I don't have it handy right now, but I'll bring it next week. But the interesting thing about the knuckle brace was that it was printed so it was fairly thin and it had this sort of like this mesh structure. And then what I did was that it's printed so it's roughly the right size. But then what you do is that you soak it in hot water or you use a heat gun, and then you could use that to mold the shape. So I would recommend using the calipers to get in the ballpark, and then what you do is that you give it the heat gun treatment to get it to where you want. Another thing that you could do is that if you want to turn it into like, that sort of like that Voronoi mesh shape, there's a tool from Autodesk called Mesh Mixer. So I would recommend looking up the Voronoi tutorials on Mesh Mixer, and that may actually help you sort of convert your model into something that's a little bit more pliable, that's a little bit more, that would take a little bit better to sort of reshaping, and that would actually probably be a pretty good way to go. Email me if you can't find any of that information, and I can just send it to you. That's not a problem. But yeah, absolutely. I mean, given the fact that, and in fact, I'm going to be touching on material stuff in a second as well. Materials do make a difference to the result, and PLA is a really interesting thing that, it stays pretty hard, but it is a kind of thermoplastic. You don't need things to be too hot for you to be able to reshape it, which can both be amazing and it can be kind of a pain in the bum as well. So, but yeah.
The one thing I read about PLA, and that's the only thing I can print with my current printer, but it's the
sure.
It doesn't withstand well water because it's still very porous.
Correct, yeah. So you probably don't want to keep it too soaked for too long. But all that said, I used it to print a replacement bathroom door handle. I've had that for a few months now and I haven't had any problems, like none. Even the screw for it, because I'm pathological with this sort of thing, even the screw for it is printed out of plastic. It's so far held up. So I wouldn't worry too much about that. I'd probably say I'd look at if you have situations where it's immersed in water all the time, okay, yeah, that may be a problem. But if it's getting the occasional splash of water, or even if it's in a moist environment, I think it takes a fairly long time. We're talking about months and months and months and months worth of exposure, maybe even years, before it really starts to sort of become a problem. Again, it also partially depends on the PLA, partially depends on the design, depends on the infill and how thick you made the walls, all of that. So there's a whole bunch of factors which come into play for that. Cool. Of course, no worries. So let's go into sort of like having a quick look at some modeling choices. So let me find my thing just here. So what I want to do is I want to start with, let me just go backwards with this a little bit. Let me just delete what I don't need. Okay, let's start with this cube. So I'm going to change this to the desk share. Okay, so first thing I want to show you is, I know we covered this last week, but it bears repeating. What happens if you have an object and you have faces in different directions? What happens to the detail that's on the object? So I had this this torture cube which I printed. So I have this cube here, and I put a star on the top, star on the side, and a star on the bottom. And I printed it with scaffolding. So what happens to the level of detail? And I thought that was, it more or less did what I expected, right? So just looking at it from the side, you can see what the results kind of look like, right? So let me just bring that into the center here and focus in on it a bit. So the top looks pretty good, right? So the print quality is pretty much what you'd expect. It's pretty sharp, and even the side was surprisingly good. I thought that this would have a couple of printing artifacts, but it actually came out pretty nicely. I don't think I've got anything to complain about that. But the bottom is a mess. It's just tragic, right? And it's partially down to scaffolds being attached, but it's partially just gone down to sort of like when we're trying to print those bottom layers and we're trying to print the scaffolding at the same time, anything that's facing down, if you have a lot of detail there, it's going to get mushed up. And this is difficult to recover. I mean, you may want to have a go at this with a soldering iron a little bit, I guess, to sort of like rebend the plastic and try to remelt it all together. But you run the risk of, especially with something that small, warping the whole thing, right? Because it conducts heats fairly well, and you'll very quickly end up sort of like melting the whole thing. So it's important to note that things that are facing down are not going to be super amazing, and there are other things that come into play as well, right? So let me switch back to the desktop here. So another thing that I did was that, sorry, I have a mini extra. I was using this earlier today as some examples. I have a cube here, and I printed out 2 cubes. So I printed out 1 cube over here, and then what I did was that I took this cube and I used this cage to, let me just actually group it all together again. Group that, and then what I'm going to do is I'm going to move it over, hopefully, and maybe this will all line up. So I took this, I basically had this cube, and then I made a little cage that was made out of triangular prisms, and I used that to fake beveling. So, I took that same cube and I beveled the edges of it. Why did I do that? And the reason I did that was that you do see some interesting artifacts when you are using, especially when you're using an FDM printer. And what happens is that you end up with this odd sort of like pinching artifacts on the edges of objects, right? So let me just show you this cube just here. So when we've got this cube, it looks pretty great, right? But if you look, you can just barely see the light catching it. What happens is that when you've got sharp edges on the objects, they pinch. They actually stick out a little bit, right? So because of how it cools, and even on the top you see it a little bit, right? You end up with these edges of the objects, and they don't actually end up flat. They end up actually sticking out of the surface a little bit, because as it cools, what will happen is that surface will just sort of pinch just a little bit and stick out. And anywhere that you've got like super sharp edges between flat surfaces, that you start getting these sort of pinching issues. This edge is like a really solid example of that. And that's partially got to do with the fact that, like, when these are printing out, the print head can't turn a corner all that fast, right? It's partially got to do with how sort of like fast it cools as well. You end up with some like odd sort of like thermal problems. But you don't see that problem when you bevel the edges, right? So wherever you can, if you can bevel the edges of the object, the dimensional accuracy will be significantly better, especially if you've got it attached to sort of like big old flat surfaces. So this is quite nice. There aren't any sort of like measurement issues. So I had to go with the calipers, and it's a little bit more accurate than this one. And it's only sticking out 0.1 of a millimeter, but if you're fitting parts together, that sort of thing can make quite a difference, right? So especially if you're fitting big parts together. So if you're after sort of like stuff that works with the 3D printer in terms of getting sort of a nice sharp result, that's something that you probably want to pay attention to, and wherever you can, cut those edges out. And I know it's sort of like difficult to do in practice. One quick thing that we discovered a little earlier today is that in Tinkercad, you can actually do that automatically with some of the objects that it provides you. So if you mess around with if you import a cube and you mess around with the radius parameter, you can actually round those edges on the objects a bit. And that's actually really, really, really nice. So it's something I would consider doing if you've got objects and you don't mind sort of like the organic shape on them. That makes them a little bit better to work with, and it works a little bit better with the printer. The last thing that I wanted to show you just on this topic was this odd little, so another sort of like torture test object that I've done here. So you can see part of it is lying down, part of it's at 45 degrees, and part of it's sort of sticking straight up. And let me show you that on the overhead camera. And this is what it looks like. So what's key about this is what happens to each one of these in terms of accuracy. So for the part that was lying down on the print bed, it's actually fairly dimensionally accurate, right? So, and it's actually quite thin. So on that particular part of the object that's here, let me see if I can back this out a little bit and I'll get this a little bit sharper. Let me turn the light back on again. Okay, there we go. So when we've got the base of this object just here, what'll happen is that because this side is facing down on the print, the print bed is just here, it can go very, very tiny steps going up, and so it maintains the accuracy of the print in that dimension. But around the edge of that little tooth, it's a little bit blobby. And when you have the top of the object where you're going up off the build plate, so we're going up like this, we end up with the opposite problem. So it's a little bit thick because the print head is traveling around in this direction, but it's much more square, right? So this side of the object is sort of square. And the pathological case in between is when you're dealing with the 45-degree angle. And when you're dealing with that 45-degree angle, you can see that it's, let me just get the light in the focus here a little bit better. There we go. you can see that there are lots of little striations there, and it bends a bit, and that just doesn't come out all that well, right? So again, just sort of like re-emphasizing part orientation and which way around you have things and how much you have facing off the build plate makes a big difference in terms of how accurate it's going to be. So if you're printing fine things, if you're printing fine details, try to sort of align them with the plate if you can, because that will give you the highest amount of detail. And this is going to be coupled with what we're going to talk about next week in terms of how do you split your model up for printing and how do you make sure that you maintain the right level of detail for everything that's going to be in your print. Okay, cool. Let's go to the next slide. Okay, let's talk a little bit about material choices. So as far as material choices go, just touching on this very briefly, the primary plastic that most people use is PLA. It's cheaply available. It's a bioplastic, which is remarkable. It really is made from plants, so it's quite environmentally friendly. It's also compostable. So if your city compost heap has a high enough temperature heap, so for example the one in San Francisco does, you can throw it in the compost and it will break down. It's kind of crazy, but there aren't many plastics you can throw in the bin for composting, but this is totally one of them. But it has temperature issues. If things get too warm, it does warp. At roughly about sort of like 80 to 90 degrees Celsius, it starts getting a little bit wibbly. So it's not the best choice for those kinds of applications. If the moisture is really high all the time, it can also start warping. So that's a potential problem. And if it's in like a hot, wet environment, it will start to biodegrade. So that can be a little bit of a problem. So there are other plastic options that are available. The one that's sort of like in between in terms of price and hardness and environmental friendliness is PETG. PETG is often made from recycled plastic bottles. So it's relatively environmentally friendly. It's much harder than PLA. Works at a slightly higher temperature, and it's much more stiff. So it's actually really good if you're printing transparent objects, for example. So if you're really, 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 really keen, you could probably even print a lens out of PETG. I tried that once. It was an interesting experiment, but that's another story. But you can totally sort of like print these hard objects, and it's sort of like slightly syrup like. So if you want to sort of, especially if you're printing something with 100% infill, it will blend quite nicely without too many artifacts. So it's quite good. The far end of the scale is ABS. So it's a high impact plastic. It's what you see in most consumer products and most consumer plastics. They're made up of ABS. ABS is very hard. It's very light. It's also kind of expensive. When you print it, it lets off slightly toxic fumes. So when you're printing it, make sure that you're in a relatively well ventilated environment. But it is a great plastic. It's very, very, very stiff. Not very environmentally friendly. But it's a good choice if you want to finish something. If you are, if you're done with your design and you want to make something that's going to last for a long time, you can print it out of ABS. There's also sort of other sort of like exotic kind of plastics that you can print. TPU is one of them. It basically prints like soft rubber. It is really weird. So you can print tires out of it. I printed camera bellows out of it because it was flexible. It's kind of weird, but it's very cool. But as you start getting into these sort of like exotic filaments, you have issues with them clogging the printer nozzle, because they behave in very sort of strange ways, especially at high temperatures. So if you're using a lot of different exotic plastics, you then end up having to do more maintenance on your printer because you end up having to clean it more often. You end up having to clean out the nozzle because they get clogged with these odd kind of filaments. Another odd one was wood or bamboo. So you can actually print this filament that is it's plastic, but within it is a very high concentration of wood and bamboo. So when you're printing, it smells like a wood shop. And once you're finished with your print, you can sand it, and then you can even stain it like wood, which is really crazy. And you can end up with other types of like odd filaments. You can get ones that have flecks of brass that are in it, so you end up with a very sort of like metal-like finish. You can also get flecks of like gold and silver-like material as well, if that's the kind of thing you're into. So it's you totally have sort of like other options there. And if you want to, the nice thing about those kinds of filament is that they're good if you don't want to spend a lot of time finishing your print, and you don't want to like sand it and you don't want to paint it. They're a good way of sort of making something sculptural without having to go through all those extra finishing steps. Cool. before I get into mechanisms, maybe I'm actually just going to rearrange things a little bit. Do we have any questions?
So I just bought some wood PLA just to test it. I haven't tried it yet. It just arrived a couple of days ago. That only has like a 20% wood. Is that the one that you were referring, or?
Yeah, that's it. Yeah, yeah.
Okay.
I mean, like when I say like a high concentration of wood, like 20% to me.
Yeah, it's
like
still
a lot.
it's still plastic. Yeah.
Yeah. But you know,
Cool.
like
Yeah,
I said,
I look forward to trying it.
Yeah, and like I said, you can totally stain it, which is just the weirdest thing. You'd think it wouldn't take, but it actually takes fairly well. And like I don't know, if you're into it, the smell is kind of amazing while you're printing. So I don't know, it may be vaguely toxic. I don't know, but it seems nice to me. So yeah.
Does the wood PLA last longer than the PLA on its own?
I honestly
because you
don't
said
know.
the PLA. Oh, okay.
Yeah, I don't know. I mean, they're both sort of like biomaterials, right? So you've got wood and you've got PLA, which is like a plant plastic. So I don't know. And I don't know whether I can fairly compare like, PLA to sort of like, the compostable spoons you get. I guess they're sort of like distant cousins, but
Right.
but functionally they are different. So yeah. But yeah, I mean, like I said, PLA, like I said, PLA is one of those things that you can use and you can feel sort of like reasonably environmentally conscious about it. And I think the other thing is that it's possible to make PLA pieces that last for a long time. I actually, a while ago, I think it's like approaching a year at this point, I submitted a sculpture to a contest. So there's a there's a donut shop that I'm extremely fond of in San Francisco, and they'll do like an art competition every year, or it's every couple of years, and they had an art competition. It's like, no way, I'm not going to miss out on this. So I ended up making something out of I basically ended up making something sculptural out of PLA. It was like a donut that was impaled on the Sutro Tower. Weird story, but anyway, whatever. I ended up making it out of PLA, but then what I did was that I was concerned about how long is this thing going to last? But so far it's been up on the wall for ages, no problems. And the other thing is that I spent some time finishing it, right? So I put several layers of paint on it. I sanded it. I made sure that it was as sealed as well as I could. So I'm fairly confident that it's going to last a while. Hopefully it won't biodegrade on the wall there. Perhaps should have thought it through a little bit more, but I was in a little bit of a hurry to submit. But it all depends. But so far in practice, these things have lasted quite a while, so I haven't had any problems so far. Cool. All right, on to the very next thing. Sorry, was that a question?
Yep.
Oh, we're all good? Okay, awesome. Okay, let's talk. We're running a little bit short on time, so I'm not gonna rush through this, but we should just get on with it. Let's talk a little bit about mechanisms. So joints, hinges, hingles? What am I thinking? I should really fix that. Hinges, sorry. Joints, hinges, and axles, right? So let's talk a little bit about those, right? So I'm going to go through a couple of super quick examples, right? So let me just bring up the this again. So okay, so what I wanted to do was that I want to show you really just two examples, but I think they're kind of illustrative. So what I wanted to do was that I wanted to first of all just show you a joint, if you like, right? So a joint that goes around an axle. So what I did was that a good sort of like when you're experimenting with this in practice, when you're using 3D printers at home, I found that if you work with cylinders that are 6 millimeters in diameter, that works the best. Just in terms of it's the right trade-off between, it's not so small that you get drowned in the level of detail that the printer can print, and it's not so big that you have to wait ages before the printer prints something before you can work on an iteration of it, right? So I generally work around 6 millimeter axles when I'm doing experimental stuff because it's like I said, it seems to be the right balance, at least for me, when I'm doing this sort of thing. So what I wanted to do was that I wanted to take this axle and I wanted to build a little arm that went around it. So I've got two super quick examples of what I did with that. So I'm just going to ungroup this. So what I did was that the actual arm part of the axle is relatively simple. So what I've got is that I've got a little sort of box for the arm, a normal just cylinder, I made this 4 millimeters high, another sort of like, 4 to 6 millimeters seems to be the right range for this sort of thing. And then what I did was that I carved a hole out of it just using another cylinder, but I made sure the cylinder diameter was about 0.1 millimeters bigger than in both dimensions. So I guess like 0.2 millimeters on each side, bigger than the actual axle here itself. Because if you made it the same size, the two won't click together at all, right? You need to give it a little bit of room to move. And then I used the object in the library of shape is the roof. So I used the roof object here to carve out the actual open part of the axle, and then I stuck it on. I then, and that was okay, but I wanted to refine that a little bit. So remember I said, like, bevel wherever you can. So I took that same design and I just beveled it ever so slightly. And the way that I did that was that I used a couple of cones. So I dragged in the cone objects, changed them to holes. And then what I did was that I just moved them so they just bit into the top of it, just ever so slightly. So we ended up with a nice sort of like rounded side on this. And those were that's it. That's a little shape here. So I've got, I've got this little library of parts, right? So I've got an axle here and I've got an arm. And then what I can do is that I can just use those parts to make a hinge, which is exactly what I did here, right? So, I took those two, I took those two arms, I connected them to just a box here, and then I took that same sort of box there, and then actually I'll show you what's going on here in just a second. But I took that same box there, and then I put on a little arm, I connected it to the axle here, I made sure that there's a nice sort of like big gap here so that they can rotate around. And then I made sort of like a super, super basic, super functional hinge. One little thing, it's almost like an academic point that I'm noting here, is that when I had this arm here, I needed to make sure there was enough space for this hinge to rotate. So what I then did was that I took another cylinder that was, much wider than this, but not too much wider. And I used that to initially just carve a little bite out of this so that those little arms wouldn't go colliding with that box there. And I just like the idea of having a little rounded thing here instead of having a flat edge. I mean, like another way that I could have done this is that I could have backed that flat edge off from where the arm was, but it feels a little bit neater and it looks a little bit neater. And as you go, you'll learn a little bit about how to do that, right? And it just you develop your own sort of like little library of techniques for doing that, I guess, right? So let me show you how that actually worked out. And I thought it worked out pretty well. Let me just get these bits out. So this is one of the arms that I printed out, and we've got the axle here, and they snapped it. So you get some idea of how big this is. Like 6 millimeters really is quite tiny. But it's enough to sort of start fiddling with. So I can take this and it clicks on in such a satisfying way. I just love this sound. There you go. It just sort of clicks on really nicely and it turns really nicely. There's enough room for that. About that, backing it off about 0.1 to 0.2 millimeters gives you enough space there. Again, that's one of those things you probably want to tune per printer to sort of figure out what that tolerance is. But that turns sort of like quite comfortably and quite nicely. So, when we took the hinge, same sort of thing, right? So I'm going to take this and it just clicks right on and it's a totally functional hinge, right? So, there's not too much friction here, but there's just a little bit of friction. So it doesn't like flap about when I shake it. If we did want to make it completely mobile, you could either put some grease on that, or you could actually back off that inside diameter of the cylinder so that it's a little bit more sort of free to move. So that was that hinge. Oh, Sebastian, you're on mute.
I haven't found a way to not have Tinkercad snap to the 1 millimeter. I have to go and type in the amount I want to scale something or move it by every time.
So there's this.
Oh, snap grid 1 millimeter. Okay, sorry.
That's that little thing down there. Yeah. So if you want to move things a little bit more finely, that's all right. It took me a while to find it as well. So what I do was that I'd make the object bigger. I'd scale it up like 100%.
I see it now. Yeah.
Scale it and then scale it back down. It's dumb. But anyway, yeah. So you can totally do that. And you can turn it off, but I wouldn't recommend it. It can get a little exciting. Okay. The next thing that I wanted to go into was axles. And again, they're sort of like a relatively simple design here. But here's what's important, right? So let me show you what an axle shouldn't look like. So when you're making an axle that rotates, when you're printing it, I think something that's clearly the wrong thing to do is to print it like this. If you print it like this, so your axle comes off the build plate like this, what's going to happen is that as soon as you put any load on either end of this, you have the potential of it snapping, right? Because remember, it gets built up layer by layer by layer by layer. And the amount of strength between the layers is much lower than it is along the layers, right? So what you want to do is that ideally, you'd want to be able to print the cylinder on its side. But if you print the cylinder on its side, you run into another problem. Because if you print the cylinder on its side and it's got supports underneath it, then the underside of it's going to be really rough, right? Remember, we were talking about that just earlier today, right? It's going to the bottom of it's going to be really rough, and it's going to be quite hard to work with. So I do this cheat instead, which has so far worked incredibly well. And it's one of these little hacks that I highly recommend. So what you do is that you take your cylinder, you lay it on its side, and then what you do is that you take about 10% off the top and the bottom. You can just eyeball it. Like, and I say 10%, but it could be as like 25%, whatever works for you, basically. But then what you do is that you basically shave the top and the bottom off it. I shave off the top as well, simply because I like to be symmetric, but you don't have to. So you can even just shave off one side. But basically what you want to do is that you want to flatten one side so that you can print it, and this will print without supports because those angles are quite gentle, right? At this point, right, when you get to sort of like something like this, when you're not dealing with sort of like, you know, the very edges of that circle, so that will print out quite nicely. And then your when you print it, the strength will be along the axle, right? So when you've got a wheel or load on either end of this, then it won't snap along that along that cross section, because that's where all the strength is. So then once you've done that, you know, you can start building bits that are going to snap onto it. So I'm actually going to give it a little preview next week. What you can do is that you can take that same axle shape, make it ever so slightly larger, and then you drop it into the middle of something like this, and there you go. You've got your snap-on wheel, right? It'll just like, you can get like a nice friction fit on that, and that real wheel that'll stick on it. If you've got a brush, if you've got some sort of like, you know, hole that the axle needs to go through, you can do the same thing. So you can take the same cylinder shape, make it slightly larger, and then the axle will drop straight into that. And you know, how well does this work? So let's have a quick look, right? So let me go back to the overhead camera. So when we've got our axle shape just here, let me show you the axle. So this is the axle just here. So it's not super clear, but it's printed basically in lines that are along here, so it's nice and strong. But like, you know, it goes quite nicely into the brush here. So I've got this here. I've got the axle that goes in. That fits in quite comfortably. It turns quite well. There's no weird shake because I've shaved the top and the bottom off. So, you know, that works extremely well. And then we've got I've got this little wheel thing which sort of semi-snaps on. And that, you know, that will turn with it. Again, sort of like, you know, matching the size of the hole that's underneath. And that's like a really basic wheel and axle, but that's something you can sort of like put together in Tinkercad, and it's a strong component, especially for sort of like, you know, little bits of dinky plastic that you get off a 3D printer. It can handle a reasonable amount of load without it sort of like warping or getting weird. So that's totally something that you can build in the in that system. So we've only got a couple of minutes left. No, please.
Yeah. That last piece that you snapped on the end,
yes.
That on the inside was the same shape as the axle. How did you make that hole again?
What I did was that I cheated, right? So let me just show you what I did here. So what I did was that I just took that axle shape, and then I turned it on its side, and then I changed it to a whole object here. And then what I did was that this is the important part. I used that 0.1 millimeter snap grid, and I pulled it on this corner, and then I pulled it on the opposite corner, so that, you know, it's still centered. And then I used that as a hole to sort of cut out the shape there. But there are more methodical ways of maintaining the accuracy for doing this, and I will cover that next week. Cool. So the assignment for this week is I want you to make a hinged thing. It sounds simple, but it is weirdly subtle. So I want you to make a working hinge. As a challenge, you may want to try making like a folding up thing. So I tried making a folding up box the other day. That was interesting. So see if you can, come up with your own little library of parts and see if you can make a hinge thing. And I want you to pay attention to the orientation of your object on the build plate. Like, what is it that you favor? What is it that you think is more important or less important when you are building something like this? And how can you make it work, basically? So have a go at that, and just send me your results as usual. Sort of like, if you can get it to me by Wednesday, I can probably print it so that we can chat about it for the next class. Cool.
And did you say you automatically see our stuff?
Yes.
Or how do you share it with you again?
Yeah. So I can basically keep an eye out on the student submissions, and I can see them because they're all in the same class, so to speak, like the Tinkercad classroom. So I could probably see your results, or you could just email me, right? So a good way of doing that is that you can go to, you hit the send to button, and then the bottom here, you go invite people, and then you go generate new link, and then copy link, and then that's in your clipboard, and then you can just email that to me. That's the easiest way of submitting it.
Okay.
Cool. Probably just like, I know I'm running just slightly over time, but just one thing that I probably just want to show you is I actually want to go back to sort of this nut and bolt mechanism, because it's pretty illustrative of, this whole thing about cutting out a side of the axle. It works, right? So nuts and bolts are important in that they need to take a lot of load, and you don't want the end of the bolt shearing off. So when I 3D print my bolts, I want them to be on the side. So that's exactly what I've done, right? So you can actually model bolts in Tinkercad if you want. So you can model sort of like threads, and you can take a negative of that thread and use that to sort of make a thread hole, basically. But when you're modeling the bolts as well, critically, right, printing them like this is going to be a real problem, because you don't want the end of the bolt shearing off. So by shaving the top and the bottom off it, you can print it sideways like this. And when you print it sideways like that, it has strength in all the right places. And this is the cool thing. Even though the thread is not complete, it still totally works, right? So it still quite comfortably fits on the nut here, and the nut travels completely. There's no extra weakness here. There's no strangeness. There is a gap. You can see that there, but it still functions like a nut and a bolt. And this is like an adaptation of an existing part and making it work on 3D printing. And even cheap little like 3D printers, like the Monoprice Maker Mini that I had, will print at the level of detail that's necessary for very, very, very detailed sort of like sub-millimeter threads that you have here. It's totally possible, and you can do that without supports. And my own pathology that I have with 3D printing is that I always try to print things without supports if I could possibly get away with it. It's just one of those things that's there for sort of like strength and also for detail as well. So I think when you're keeping this sort of like when you're having a go at this hinge design, keep in mind, like, how can you do this without necessarily introducing any supports? Is it even possible? So I would recommend giving that a go and just seeing what happens. Cool. All right. Any last questions before we go?
Oh, good.
Awesome. Was that little slicing technique, is that something you came up with on your own, Bhautik?
Yeah.
It's pretty cool. It's awesome to see that thread together. That's pretty amazing.
Yeah, I haven't come across anybody else who's done it, but I would be very surprised. I would be extremely surprised if it isn't documented somewhere else and somebody else hasn't done it already. It's just one of those things that I think is 3D print is a little bit. It is a little bit of a craft, right? And as you work with a medium, some things sort of like emerge from it that end up as like common understandings. And when you talk to other people who've also gone through the same thing, they've also come to the same conclusions and understandings. And it's just, I think it's one of those things that I think I would be highly surprised if folks who are sort of like, have been fiddling with 3D printing for a while haven't independently come up with something similar as well. So, and then that's why we have these classes. That's why we have these conversations, is so we can share this knowledge, and then, hopefully somebody else will come up with a neat trick and share it with us all, So, yeah.
If I my engineering studies were like 30 years ago, so you shouldn't quote me on this, but there are, even in metal, some bolts that are shaved shaved on the side.
Right.
And typically they're used in dirty environments where you have to make sure that debris and things like that get out of the way. If you're
right.
Like if there's grease or something that can collect powder or things like that, and you don't want that to trigger the mechanism, they have parts that are shaved.
There you go. That's awesome.
And it's also there's a similar thing, but it's more of a wedge that is used for self-threading stuff. But again, very distant memories for me.
It's one of those convergent evolution things. I think a lot of folks basically have a similar sort of mechanical problem, and they come up with very similar solutions. One of the things that I needed to do was that I needed to come up with a focusing mount for the back of one of the camera components that I had, and I needed to be able to turn a screw basically and have something backwards and forwards, but without turning. And it turns out that there's a whole bunch of literature and designs for doing this for situations where you want to be able to put a screw into something and get material back out. Right? So when you do that, you want to make sure that you're not compressing whatever you're screwing into the walls around it. You want to make sure that you basically drill it out, and as you put the screw in, it will cause the material to eject as well.
Yeah.
Yes. So
I've drilled holes in the ground with a motorized thing to put posts in. Yeah.
That's right. Yeah. So and they use like specialized, and I did a similar sort of thing. So I basically had a screw with a gap in it, but then what I did was that because the gap doesn't turn, I actually put the mount for the thing that I needed not to turn into that hole. So there's all sorts of you discover all these things, and they're kind of fun to work with. It's a really good time. Yeah. Cool. Awesome. Well, thank you, everyone. Like I said, no rush on the assignments. We'll chat a little bit more. And next week, what we're going to do is we're going to get into accuracy, and we're going to get into breaking models into smaller pieces. I think that one's going to be extremely useful for a lot of you folks. It's going to be a good time. All right. Thanks, everyone. Have a good week. Take it easy. All right. No worries. Bye.